Hello everyone, my name is Ubaidullah Hafiz and this presentation is about Ceer, which uses empirical analysis to predict optimal GPU instances for a given CNN. Let's get started. Deep neural nets are being used in a large variety of applications ranging from healthcare, stock exchange, cloud services, or even social media and many more. However, not all DNNs are the same. For example, CNNs are more extensively used in healthcare, social media, and advertisements. Figure on the right shows the high-level structure of a popular CNN Inception V3. CNNs are primarily composed of convolution pooling and fully connected layers, which makes them suited for regular grid-like data, for example, images. However, training CNNs on large datasets is very compute intensive. For example, training Inception V3 for one epoch of popular ImageNet data takes a few days on a commodity CPU, a few hours on a single GPU, and can be done in less than an hour when using multiple GPUs. But GPUs are expensive. However, one can rent cloud instances of GPUs for a fraction of a cost. Here is the comparison of cost of buying a GPU-equipped server versus renting it for CNN training. Table shows the cost comparison of NVIDIA V100 GPU server, which is one of the latest GPUs being used for CNN training. We see that training can be done in as low as $9 when renting on AWS as compared to $35,000 upfront cost of buying a 4 GPU machine. Also, GPU equipped machines consume a lot of power. A GPU server roughly consumes power varying between 1200 to 1500 watts. Each GPU typically consumes 200 to 300 watts of power. Cloud providers typically offer a variety of GPU instances. Table shows some of the offerings from Amazon Web Services. Typically, an expensive instance has larger T-flops, but that does not translate directly to faster training, or using a cheaper GPU may not directly translate into cost savings. For example, in our experiments, we found out that training AlexNet is cheapest as well as fastest on G4 instances, even though G4 is not the most expensive instance available. However, for Inception V3, training is fastest when using P3 instances, but cheapest when using G4 instances. Hence, deciding which GPU instance to use for a given model is not straightforward. To summarize the challenges, first, different GPU instances are optimal for different models. For example, for AlexNet, G4 is optimal. Second, even for the same model, different instances are optimal depending on the goal. For example, if we want to minimize the cost, G4 is optimal for Inception V3, and if we want to minimize training time, P3 is optimal for Inception V3. Another possible scenario could be a limit on the budget for training, and we want to maximize performance staying within the budget. Given the above challenges, we propose that if we can accurately predict training time for a given CNN across all available GPU resources, we can predict cost of training across all resources as well. These predictions can help in picking optimal resources for a given CNN and a given goal. Here is the outline for the rest of the doc. First, I will briefly explain how CNNs are represented computationally in modern DNN training frameworks. Then we will talk how Ceer uses that representation to predict training times for given CNN. After that, we will evaluate the performance of Ceer, and then we will conclude after discussing some future work and limitations of Ceer. Let's start with CNN representation in modern DNN training frameworks. Modern DNN training frameworks such as TensorFlow or PyTorch represent CNN training jobs as data flow graphs. In a data flow graph representation of CNN, each node represents some compute operation, either for a CPU device or a GPU device, and each edge shows some data flow. All incoming edges should be satisfied for an operation to execute. For example, figure on the right side shows a data flow graph. Blue numbers inside each node shows how much time each compute operation will take. Numbers along the edge shows how much data is being transferred from each node to its successors. These edges incur communication overhead when adjacent nodes are placed on different devices. For example, in the example graph, if the first node with 21 compute time is placed on CPU and its adjacent node with 54 is placed on GPU, communication overhead will be incurred to transfer data from CPU to GPU. These graphs are always DAGs for CNNs. Just to give an idea about the size of these graphs for the CNNs we experiment with, this graph size varies from 500 to 5,000 nodes for different CNNs. Now, we will move on to discussing how the data flow graph is being used by Ceer for predicting accurate training times. In our experiments, we found some key insights about CNN training. For all the CNNs we tested, training always consisted of a small set of unique operations. These operations can be classified into three categories. First, heavy GPU operations are the operations which constitute most of the training time. Each individual operation of this type also have higher compute times as compared to rest of the operation types. And another type of GPU operations are light GPU operations. These operations have comparatively small compute times and tend to have higher variance in compute times for the same input size. There are also few operations which must be executed on CPU. These operations also have very small compute times. For a given heavy operation type and input size, heavy operations have very low variance in compute times and hence can be predicted. GPUs typically execute one operation at a time. Therefore, a linear additive model using estimated compute times for different operations can result in accurate prediction of total training time. Based on the insights discussed, Ceer's estimation models make use of the fact that if we can estimate compute times of individual operations accurately, we can predict training time for a given CNN. This equation shows Ceer's prediction model. It's a linear additive model where T is the total predicted time and N is the total number of operations, and the term inside summation, that is T GPU op I input of I, is the estimated compute time for the ith operation for a given input size. The term in parentheses can estimate the time for each training step, and then we multiply this with the number of training iterations, which is the ratio of total training samples and the number of samples in each batch of training. Next, we will discuss how Ceer estimates the compute time for each operation in the CNN graph. As we saw that there are three different types of operations in CNN graph, Ceer uses a different modeling approach for each type of operation. Heavy operations are modeled using linear model based on the size of all the input variables. A different linear model is used for each heavy operation. The figure on the right side shows different linear models used for two different heavy operations, that are ReLU and average pool gradient. Almost all the light GPU operations take a similar amount of time on average, but since compute times of these operations are very low, they usually have high variance in compute time, so a constant median-based model is used for light GPU operations. A similar but a separate model is used for modeling CPU operations. One thing to note here is that this model does not take into account any communication overheads and hence only works for single GPU training. Let's now extend this model for a data parallel setting in which multiple GPUs are being used. Our experiments show that running a model on multiple GPUs using data parallelism has some overhead. We observed that this overhead is linearly dependent on a few characteristics of the model as well as the GPU server. Graph on the right shows the relationship between the number of model parameters of the CNN model when two GPUs are being used. From this graph, we see that the overhead of data parallelism is linearly dependent on the number of model parameters. Another thing to note here is that slope of each line is different, which depends on the bandwidth available in the GPU instance. Based on these factors, Ceer's new model has a new factor K, which is the number of GPUs, and another term highlighted in the equation is added to take into account the overhead of data parallelism. This new term is function of model This new term is function of model parameters, number of GPUs, as well as the bandwidth available across each pair of GPUs. This concludes our discussion about Ceer's design. In the next section, we will evaluate performance of Ceer. First, we will evaluate how accurate training time predictions are for Ceer. Graph below shows comparison of actual training times versus predicted training times for four different models across 4 different GPU instances. Here, the number of GPUs used is fixed to 4 for all instances. In our experiments, we observed that the average prediction error is about 5.6%, which is quite low. In the last result, we saw that Ceer can accurately predict training time for a given CNN. Training time prediction can be used to estimate the cost of training. Consider another scenario in which we want to minimize the cost of training Inception V3. Graph shows the performance across different GPU types. The hourly rate of one GPU of P2 instance is the cheapest, and the hourly rate of picking 4 GPU instances of P3 is highest. We see that most cost-effective from the graph is using one GPU for G4 instance, and that's what Ceer predicts as well. Here is another result for the case when we don't want our budget to exceed $3 an hour. Within $3 an hour, we can either get 3 GPUs of P2, or 3 GPUs of G3, or 3 GPUs of G4, or 1 GPU of P3. Graph below shows comparison of the above 4 configurations for 4 different models. We see that picking the latest GPU strategy accurately predicts the fastest training GPU setups for Inception V3 and VGG19. However, Ceer can reduce training time by 91% for LXNet and by 27% for ResNet by picking G4 setup instead, resulting in an average cost saving of about 29%. Next, let's talk about future work and limitations of Ceer. For predictions, Ceer depends on historical data. If an operation type is not seen by Ceer already, it cannot predict its compute time. However, benchmarking a few new operations instead of running the DNN training is generally not very expensive. As of now, Ceer's communication model is limited to one single host. It can be modified to support multiple machines or multiple communication links with varying bandwidths. Linear additive model of Ceer for training time prediction works for data-parallelism and may not be able to predict accurately for model distributed training. Ceer in its current implementation is limited to CNNs and may not be generalizable to all types of DNNs. Also, in its current implementation, Ceer only supports TensorFlow and no other DNN training frameworks such as PyTorch, etc. To conclude, Ceer takes the CNN compute graph as input and uses a simple linear model to predict training time to estimate the training cost of a given CNN across different GPU types and allocate optimal number and type of resources for the given model, as well as the goal, be it cost minimization or training time minimization or some budget constraint. Thank you all for listening.